Hello, so in this video, uh, I'm going to be deriving the Crank-Nicolson uh, differencing scheme. And so pretty much this will relate to previous videos I've done. And in those previous videos, I stated we have temperatures at some time in some position j. So for instance, n plus 1 will be the next upcoming time. So essentially for this equation right here, it looks very similar to previous ones we have worked with, except up to about this point. Now we have a little extra stuff in which we relate the next position with the next time minus 2. There should be a t right there. Yeah, there should be like a capital T right there. And that is the temperature at the next position at the current time, plus the temperature at the previous position the next time. And it's over 2 to sort of take the average. So what we are going to do is, first of all, we could distribute the 2 out. And if we did that, it'd be like taking a half out and multiplying it by this. So we would have alpha delta t over 2 delta x squared. Oh my, I wrote that very crooked. This is an x squared. And alpha is the thermal diffusivity. Lowercase t is time, x is position. So now what we can do is first I'm going to erase all of this since it's been on the screen for a while and I need all the space I can have. So now what we will have is negative r, and that little portion I pulled out, we are going to have that set equal to r. So whenever we reference r, it's like, having that little section. It's a lot easier and faster to just say it equals r and just write one letter as opposed to this massive bulky fraction. So we'll have negative r t of j plus 1 n plus 1. We're going to add 1 plus 2r tj n plus 1. We're going to minus r t j minus 1 n plus 1. And that equals sign. I apologize if things look a little crooked. I'm writing kind of sideways. So here we have temperature of the next position at the next time plus 1 plus 2r of 2 times the current position at the next time minus r times t of the previous position at the next time. And I'm going to say what it equals under it because I'm going to end up running out of room over here. So this will equal RT j plus 1n. I'm just going to explain what it is after I write it, so that way it's faster. So we have this equal to r times temperature at the next position at the current time minus 1 plus 2r of the current temperature at the current time and position plus r times temperature of the previous position but at the current time. So with some algebra, we are able to say I think I have enough room to write under. I'll erase anyways, just in case. So with some algebra, we can distribute some values into this. So if we were to pull out t, j, n plus 1, we would have so here we have negative rk delta x plus 1 plus 2r minus re to the negative ik delta x. And this is all going to be equal to so on the right side, we're going to pull out temperature at the current position and current time. And we are going to have it equal to temperature at the current position, current time, all multiplied by re to the ik delta x plus 1 minus 2r plus re to the negative ik delta x. So from here, I'll erase this again as well because this is a long process. So from here, we can get the temperature at the current position, but the next time alone on the left side. So it's like we're dividing what was with it over onto the right side. So what we will end up getting is we will get 2, well, I'll just say it all after I write it. So in the numerator, we are going to get 2 times r of cosine k delta x plus 1 minus 2r. And in the denominator, we're going to get we are going to get 1 plus 2r minus 2r cosine k delta x. So, the 2 cosine k delta x's comes from something we did in a previous video. And now, I feel like I'm missing something. Yes, I am missing something. So I forgot in the front, this all should be multiplied by the temperature at the current position. But yeah, so T subscript J is what this all should be multiplied by. Normally I'd put it in the front, but I forgot it. So now what we are going to want to do is kind of test for the R values. So if we rewrite this, make it easier to test for, first of all, right? So I'm also going to write the TJ in the front because it just looks nicer. And if we have 1 minus 2r plus no, that's not. Oh, 1 minus cosine k delta x. So in the numerator we have 1 minus 2r times 1 minus cosine k delta x. And in the denominator we will have something similar. So in the denominator, we have essentially the same thing, except we have 1 plus 2r and 1 minus cosine k delta x. And the important part is this portion, which are the same portions. So essentially what we want is, yes, Avram. We want TJ so what we are going to make this value equal y, each of these values, so it's easier to kind of see, and since they equal each other, it doesn't really matter. I mean, we could say we want it equal to w or something like that, but we're just going to use y. So we are going to have 1 minus 2r times y. And on bottom we are going to have 1 plus 2r times y. And so for this, we want y is greater than 0. Wow, what is 0? Much better. So what we can further do is we can make 2ry equal to something. So if we have, do I have room? Yes, I do. We can have 2ry equal to a to make it even easier to see. So if we did that, we would have TJ, yes, you can see it, times 1 minus y, and then 1 plus y. Not y, a. And so for this, a must be greater than 0 but less than 1. So now what we can do is we can now state the boundaries for dr, which are, it must be greater than 0 and less than 1. So we have so in the end we have that r, which is alpha times delta t, change in time, divided by 2 times delta x squared, which is change in position. Well, I dropped my marker. Must be greater than 0, but also less than 1.